Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Materials and their properties from the paper Functional Materials. So students, let us see what we are going to learn in this module. First, the classification of multiferroic materials. Second, we will study that the multiferroics can be classified into type 1 and type 2 multiferroics. Thirdly, we will study their structure, properties, and applications of some type 1 multiferroic materials like bismuth ferrite and bismuth manganite. Then we will also study about the rare earth manganites. Lastly, we will also discuss about two-phase materials. So students, let us start with a basic introduction about this module. The microscopic origin of magnetism is basically the same in all the magnets. It is the presence of localized electrons, mostly in the partially filled d or f shells of transition metal or rare earth ions, which have a corresponding localized spin or magnetic moment. Exchange interactions between the localized moments leads to the magnetic order. The situation with ferroelectrics is completely different. There are several different microscopic sources of ferroelectricity, and accordingly they lead to different types of multiferroic properties. Generally speaking, there are two groups of multiferroics, that is type 1 and type 2 multiferroics. Different examples of these types of multiferroics will be discussed in detail. Let us discuss about the classification of multiferroic materials. The multiferroic materials can be classified in various different ways. For instance, Slominski and Kupis classified them into 4 major groups, albeit a few deviations are possible. The 4 groups are: first group is that of a perovskite AbO3 structured compounds, where the B position is either fully or partially occupied by the magnetic ions. Examples are BiFeO3 or BiMnO3, etc. A large number of multiferroics belongs to this category. The most well-known member is bismuth ferrite, which has high ferroelectric and ferromagnetic Curie temperatures, making it an attractive compound for applications. There are other materials too which belongs to this family, such as complex perovskite-like layered compounds with a general formula Am+1 BmO3m plus 3, where A cation can be barium, calcium, strontium, or bismuth, while B cation is either titanium, iron, nickel, or molybdenum. Second set of materials belongs to hexagonal structured rare earth manganites, depicted as RMnO3, where R could be either HO, TB, ER, YB, LU, SC, or Y. These compounds exhibit reasonably good ferroelectric characteristics and antiferromagnetic or weak ferromagnetic behavior. The most famous material belonging to this group is yttrium manganese oxide or YMnO3. Third group of materials belongs to borosides, which are compounds with chemical formula M3B7O13X, where M is a bivalent metal ion such as chromium, manganese, iron, cobalt, nickel, and copper, while X is an anion such as chlorine, bromine, or iodine. These compounds exhibit ferroelectricity along with antiferromagnetic or weakly ferromagnetic behavior. Fourth category of materials is depicted by a general formula BaMF4, where M is a metal ion such as magnesium, manganese, iron, cobalt, nickel, or zinc. These compounds are either pyroelectric or ferroelectric and also exhibit antiferromagnetic or weak ferromagnetic characteristics at low temperatures. So students, let us first discuss about the type 1 multiferroics. Ferroelectricity and magnetism emanate from two different sources, and hence the two effects are quite independent of each other. A small degree of coupling between the two orderings can be expected from these type of multiferroics. Basically, the examples of type 1 multiferroics are 1. Bismuth ferrite BiFeO3, second bismuth manganite BiMnO3, bismuth chromite BiCrO3, bismuth aluminium oxide BiAlO3, and lastly, or the fifth one, is the hexagonal manganites such as YMnO3. Now let us discuss about the type 2 multiferroics. In these materials, magnetism is the source of the existence of ferroelectricity, and it is typically attributed to a strong coupling between these two states. Another one is that the magnitude of polarization in these materials, it is very small, typically of the order of 10 to the power minus 2 microcurie per centimeter square. The examples of these materials are manganites such as TbMnO3, a few vanadates and tungstates, example Ni3V2O3, MnWO3, and there are certain type 2 multiferroics also, which are two-phase materials such as composites. Bismuth ferrite. One of the most studied multiferroic material is bismuth ferrite or BiFeO3 BFO, primarily because it has a very high ferroelectric transition temperature and shows G-type antiferromagnetism with cycloidal spin structure with Néel temperature of around 650 Kelvin. In its ferroelectric state, as shown in the figure, BFO possesses a rhombohedrali distorted AbO3 type perovskite structure with space group R3C having lattice parameters A is equal to 5.36 angstrom and alpha is equal to 59.348 degrees. Above the Curie temperature, the structure changes to a high symmetry cubic phase. As evident from the figure that the two neighboring oxygen octahedron undergoes opposite rotation about the 111 axis of the unit cell. This rotation causes bismuth, iron and oxygen ions in the unit cell to slightly move from their ideal positions along the 111 axis, leading to the development of a spontaneous polarization along the 111 axis of bismuth ferrite. BFO also exhibits a G-type antiferromagnetic ordering with iron magnetic moments aligning in one direction, that is, ferromagnetically within the 111 planes, whilst being oppositely oriented, that is, antiferromagnetically aligned between the adjacent 111 planes. However, presence of ferroelectric polarization and associated lattice distortion creates an incommensurate spin cycloid of periodicity around 62 nanometers, which gets superimposed on the prevailing antiferromagnetic ordering of spins. This leads to the averaging of the local canted weak ferromagnetic moments resulting from DM interaction. Bismuth ferrite variations. Now, bismuth ferrite, that is BIX-FeO3 minus 1 minus X ATiO3, where solid solutions A can be barium or lead. A few of these compositions shows the existence of both ferroelectricity and ferromagnetism, but typically they are antiferromagnetic with weak ferromagnetism. It also shows the existence of a morphotropic phase boundary around which the properties are maximized. Thin film research or the research on BFO thin films. Bismuth ferrite has been shown to be ferroelectric at room temperature. The ferroelectricity in this material is attributed to the distortion of FeO6 octahedra caused by the presence of 6s2 lone pair electrons of bismuth atoms. It possesses large remnant polarization in both the single crystal as well as thin film forms with polarization exceeding 50 microcurie per centimeter square. However, polycrystalline thin films can be leaky depending upon the method of preparation and other conditions. In contrast, polycrystalline BFO thin films exhibit a small value of ferroelectric polarization at room temperature and often weakly saturated rounded ferroelectric hysteresis loops due to high electrical leakage. There could be various reasons causing high electrical leakage in BFO. Since polycrystalline thin films on silicon are better compatible with existing silicon electronics, so in order to enhance the functionality of polycrystalline BFO films by reducing their electrical leakage, various methodologies have been suggested, such as optimization of parameters such as oxygen pressure or annealing temperature in chemical solution deposition, which affect the film formation. It has been shown that the BFO thin films fabricated in better oxygenated environment exhibit higher remnant polarization attributed to lower leakage current density and reduction in the impurity phase content. Besides making changes in the process parameters, concept of site engineering has been very successful in tailoring the properties of BFO, especially the electrical leakage and magnetic moment. There is a kind of doping also which can be used to tailor the properties of BFO. Typical ions which are used for substitution at the A site are lanthanum, neodymium, antimony, and allovalent ions such as barium, cobalt, nickel, while B site substitution are titanium and zirconium. On the other hand, while magnetic character of pure phase in single crystal form is antiferromagnetic, there have been few controversies on the origin of magnetism in BFO thin films. Often impurities like Fe2+ and other iron-borne impurities and deoxygenation can result in magnetism. The material is also prone to containing defects as well as difference valencies of iron which can alter the material's magnetic properties. Next is the periodic spin spiral results in zero magnetic moment and hence linear magnetoelectric effect averages to approximately zero. However, making chemical substitutions can also alter the properties of BFO. Now, for example, as we consider the substitution of A site cation by ions such as barium or neodymium give rise to significant magnetism in the compound, while substitution of B site cation by elements such as zirconium results in the alteration in the defect chemistry as well as change in the leakage characteristics of the material. Similarly, epitaxial constraints can also result in the breaking of spin spiral. However, reports indicate a large increase in the magnetism in BFO is still inclusive, and any such increase should be viewed with caution due to unidentified impurities, valence fluctuations, and any other extraneous effects which may have not been identified. Now let us discuss about the applications of bismuth ferrite. Use of bismuth ferrite or BFO into device form such as memory devices has been reviewed by various researchers. For example, it has been utilized in exchange bias memory devices. Exchange bias memory employs a bilayer structure of a ferromagnetic and antiferromagnetic material, with the ferromagnetic phase having a Curie temperature, that is Tc, higher than the Néel temperature or Tn of the antiferromagnetic phase. The interface between the ferromagnetic and antiferromagnetic material is cooled in the presence of static magnetic field from a temperature Ts such that it is between the Néel temperature and the Curie's temperature, such that it is cooled to such temperature such that it is greater than the or less than the Néel temperature. One observes a shift in the image hysteresis loop of the system along the field axis at T greater than or T less than Tn after performing the field cooling operations. This shift of the hysteresis loop along the field axis is termed as exchange bias. In the context of antiferromagnetic multiferroic memory devices such as BFO based memory devices, that is, the structure is like FM, that is ferromagnetic material, BFO device. The exchange bias can be utilized to observe the memory effect because one can then tune the sublattice magnetization in the antiferromagnetic layer by tuning the voltage, which would in turn control the magnetic hysteresis in the adjacent ferromagnetic layer. So, owing to the transition temperature being higher than the room temperature and a good antiferromagnetic stability of BFO, exchange bias effect has been studied in a number of systems which are BFO based FM, AFM devices. Researchers have also used BFO in memory devices based or magnetic tunnel junctions. These tunnel junctions consist of a sandwich structure where a thin, which is less than or equal to insulating layer is sandwiched between the two ferromagnetic layers. The tunneling resistance of this tunnel junction is governed by the relative alignment of the magnetic spins in the ferromagnetic layers, that is parallel in or anti-parallel. So BFO based tunnel junctions memory devices, they show quite high positive percentage magnetoresistance value. However, the downside is that the magnetoresistance effect, it disappears at a temperature greater than 200 Kelvin, which is much lower than the magnetic transition temperature, that is Curie's temperature or Tc. However, there is a need to study the magnetic tunnel junctions with other ferroelectric materials along with BFO, which could perhaps result in the interesting outcomes at temperatures close to the room temperature. Bismuth manganite, that is BiMnO3. It is an interesting multiferroic material with a distorted perovskite structure with monoclinically distorted unit cell having unit cell parameters A, B and C and beta is equal to 110.60 degrees. This structure is yielded when the MnO6 octahedra in otherwise simple cubic perovskite structure undergo distortion and rotation. It is also one of the very few ferromagnetic multiferroic materials and shows a collinear ferromagnetic structure with magnetic spins aligned along 010 axis. The material exhibits the magnetic moment of 3.2 μb. Bismuth manganite is an electrical insulator and is a room temperature ferroelectric. The material shows the ferromagnetic ordering below a transition temperature of 105 Kelvin. It exhibits a perovskite-based triclinic crystal structure which upon heating transforms to monoclinic structure at 450 Kelvin, followed by a transformation to non-ferroelectric orthorhombic structured phase at 770 Kelvin, which is the ferroelectric Curie temperature. The origin of ferroelectricity in BiMnO3 has been a matter of debate. Conventional thinking has been that these compounds possesses a non-centrosymmetric crystal structure with C2 space group. This allows the existence of ferroelectricity in the material. The stereochemical activity of the CS2 lone pairs of electrons on the Bi3+ site was earlier believed to be responsible for the off-center distortion which is responsible for the polar nature of BiMnO3. However, several recent theoretical and experimental investigation seems to suggest that BiMnO3 may crystallize in the centrosymmetric phase than in the non-centrosymmetric phase, with the C2 by C phase being incompatible with the ferroelectricity. In the centrosymmetric BiMnO3 structure, ferroelectricity is proposed to emanate from local non-centrosymmetry or oxygen deficient superlattice. Rare earth manganites. As evident from the figure, which shows the schematic representation of YMNO3 unit cell, showing various ionic arrangements within the structure. While six-fold coordination of oxygen is present in conventional perovskites, Mn3+ ions in hexagonal manganites have five-fold coordination. The Mn ions are at the center of MnO5 trigonal biprism formed by 5 oxygen ions. 3 of these are in a plane and remaining 2 are out of the plane. On the other hand, R-type ions have 7-fold coordination by oxygen, unlike the 12-fold or cubic coordination of A ions in a typical perovskite compound. The MnO5 biprisms are stacked along the C-axis and are arranged in space in a two-dimensional fashion. These are separated by a layer of R3+ ions stacked along the C-axis. It is interesting to note that the application of an external stimuli such as pressure and strain in thin film form can reversibly transform the hexagonal structured phase to orthorhombic structured perovskite phase, and that the hexagonal structure can be stabilized under certain process conditions. 5-fold coordination of Mn3+ ions in hexagonal RMnO3 affects the crystal field level scheme with respect to what would have been if Mn3+ ions were with the octahedral coordination. In hexagonal RMnO3 systems, 4 d electrons of Mn3+ occupies the 2 lowest states having doublet states because of splitting of d levels into low-lying doublet and an upper singlet state. Also, there is no degeneracy in the energy states, unlike Mn3+ ion in octahedral coordination. General properties of RMnO3 compounds. Hexagonal structured RMnO3 compounds also exhibit the ferroelectric to paraelectric transition at quite high temperature, typically above 500 Kelvin. In contrast, the Néel temperature of such materials is far below the room temperature. This table lists the ferroelectric and magnetic transition temperatures, spontaneous polarization, and effective paramagnetic moment for some common RMnO3 along with their structural parameters, that is A and C. The different types of two-phase forms. The figure shows the schematic of the configuration of 3 possible types of magnetoelectric or multiferroic composites. The part A represents the particles of one phase dispersed into the matrix of another phase. The B part represents the composite with alternating layers of 2 types of materials, that is a laminated composite. And lastly, the part C represents the fiber or rod type composite, where rods are of one phase and matrix of another. Two-phase magnetoelectrics. The table shows the magnetoelectric constant data for the selected two-phase magnetoelectric systems, where for a particular type of system we have the different materials and the coupling constant has been tabulated for each type of system. In the two-phase structures, one can create large changes in the magnetization owing to the strain due to the ferroelectric phase transition of the ferroelectric material during film growth, or one can also attempt to alter the magnetic structure by applying a field, the piezoelectric material, which thereby generates a strain in the magnetic material in the vicinity. Epitaxial growth of layers allows very good interfacial contact between the two materials, as in the case of barium titanate and cobalt ferrite, which has the potential to improve the coupling of parameters. So students, let us summarize what we have learnt in this module. Multiferroics, they can be classified on the origin of their phenomena, that is type 1 and type 2 multiferroics. Of the most known materials are bismuth based multiferroics, mainly the two important materials, bismuth ferrite and bismuth manganite. Both of them are type 1 multiferroics. Bismuth ferrite is the most researched material till date due to its potential for the devices attributed to its high transition temperature. However, materials show a very little coupling between the order parameter in the single phase, and they show very little magnetic moments, which limits its utility in devices. Second one is the bismuth manganite. It is a ferroelectric and ferromagnetic, but it possesses very high electrical leakage to realize its potential in devices. Next, we also discussed about the rare earth manganites, which are another class or the type 2 class of multiferroics and magnetoelectric materials. The common examples of type 2 multiferroics or rare earth manganites are RMnO3 and RMn2O5. Types of materials which typically have the hexagonal structure as their backbone. These are type 2 multiferroics and they have superior magnetoelectric coupling but have similar electric polarization. Another way to induce the magnetoelectric coupling is to artificially synthesize a mixture of ferroelectric and ferromagnetic materials which provide good quality interface either in the thin film form or in the bulk form, such as barium titanate and cobalt ferrite. Thank you.